Okay, great. Let's get started. Hello, everyone. Thank you for joining my talk. I'm Yunxiang, a PhD student at New York University. On behalf of the team, I'm excited to walk you through our project, ImageGS. As a brief overview, ImageGS is a content-adaptive image representation built on 2D Gaussians, tailored for real-time graphics applications. Now, let me share a little secret. This title slide you are looking at isn't your typical vector graphics slide. It's actually represented and rendered with ImageGS using 10,000 Gaussians. You probably didn't notice anything unusual, but if we give each Gaussian a random color, the underlying structure reveals itself. Of course, it wouldn't make much sense to store text and logos as Gaussians. Vector graphics handle those far more efficiently. Where ImageGS shines is in delivering strong quality efficiency trade-offs, enabling hardware-friendly fast random access, and supporting flexible bitrate control. It excels across a wide range of image content, from photographs and paintings to object textures and material maps, especially when features are unevenly distributed or bit rates are low. Here, the purple dots visualize a random 10% of the Gaussians, showing how ImageGS adaptively allocates resources based on the input signal. Now you might be wondering, why do we need ImageGS? Aren't existing image formats already good enough for deploying high-resolution assets in real-time graphics? Well, traditional formats like JPEG strive for rate distortion trade-offs, but their global transforms break data locality and make random access slow. Block-based compression achieves fast local decoding at the cost of modest compression ratio. More recently, neural image representations have shown impressive visual fidelity and memory efficiency, but many of them use fixed data structures that lack content adaptivity and flexible bitrate control, or rely on compute-heavy implicit neural models that are slow to decode. So, how does ImageGS address these challenges? Our representation is, in fact, incredibly simple. Much like 3D Gaussian splatting, each Gaussian primitive in ImageGS is defined by its position, scale, and rotation in image space. Since we don't need to model any view-dependent effects, the appearance information simplifies to a diffuse color vector with the same number of channels as the input. While 3D Gaussian splatting requires an opacity term to handle depth-sorted occlusions and enforce multi-view consistency, none of that is necessary in 2D. In our case, an image of colored Gaussian blobs can be rendered simply by summing their weighted colors, and the result is invariant to the order in which the Gaussians are applied. Building on this insight, we modify the point-based alpha blending equation into a simple additive form for rendering. Now there's a catch. In this naive form, every pixel would be influenced by all Gaussians, which kills rendering efficiency. Even worse, this dense pixel Gaussian correlation breaks data locality, something we absolutely need for fast local decoding. To address this, we adopt a tile-based rendering approach and limit the number of Gaussians that can contribute to any given pixel. For each Gaussian, we compute the minimum enclosing circle of its 3 standard deviation range and check tile circle intersections to assign Gaussians to tiles. Then for each pixel location X in a tile, we rank its assigned Gaussians by their evaluated value at X and keep only the top K. After normalizing the weights of the K remaining Gaussians, we arrive at the final rendering equation for ImageGS. Building on this differentiable renderer, we can now optimize a set of 2D Gaussians to reconstruct a target image. Unlike neural representations that involve implicit models, ImageGS consists entirely of explicit, physically meaningful components. This allows us to leverage various types of task-relevant information, such as image gradients or saliency maps, to guide Gaussian position initialization for faster and better convergence. Here's what the Gaussians look at initialization. Now, let's look at a runtime demo showing how quickly ImageGS converges on high-resolution images. Notice how the Gaussians rapidly capture the main structures before refining fine details over time. In addition to the initially introduced Gaussians, We also progressively add new ones in regions with high reconstruction error. We do this by sampling pixels based on their error magnitude and initializing new Gaussians at those locations. With error-guided progressive optimization, ImageGS naturally constructs a smooth level of detail hierarchy in a single run without additional overhead. This enables flexible bitrate control that adapts to device capabilities at deployment. It also facilitates quality-driven compression, where Gaussians are progressively added until the desired quality is met. Here's a smooth level of detail generated by ImageGS for 3 4K by 4K texture stacks that define an object's appearance. As you watch, notice how the textures smoothly transition from coarse to fine detail. Since existing image datasets mainly focus on natural images and contain few high-resolution samples, we built a custom dataset of 2K by 2K images spanning both photorealistic and stylized content for our evaluation. We compared ImageGS against 7 baselines, 3 implicit neural models, 2 hybrid methods, JPEG, and a concurrent work that also leverages 2D Gaussians. In these examples, ImageGS preserves fine details while producing cleaner reconstructions with fewer artifacts. Quantitative results confirm that ImageGS achieves consistently higher visual fidelity at low bit rates. For texture compression, we evaluated on 19 2K by 2K texture stacks, each with 9 channels, including diffuse color, normal, ambient occlusion, roughness, and metawness. ImageGS performs on par with or better than industry-standard GPU texture compressors, such as BC1, BC7, and ASTC. Thanks to the low-pass nature of Gaussian functions, ImageGS is also remarkably robust to pixel-level distortions and artifacts at low bit rates. As shown in these images, it removes most camera sensor noise and JPEG artifacts from the input images while preserving fine details, effectively achieving joint image compression and restoration at low bit rates. As mentioned earlier, the explicit nature of ImageGS makes it easy to incorporate additional information for guiding Gaussian allocation across the image domain so that task-specific content can be better preserved at constrained bit rates. Here, the results show that by leveraging visual saliency guidance, ImageGS better preserves semantic image features and maintains more consistent visual question answering performance than the JPEG baseline at low bit rates. And that wraps up my talk. Thank you all for being here. I hope you found it interesting and enjoyable. Thank you.